All right, the next class of transformations I want to talk about are reflections. And let's just focus on the 2D plane for now. So by a reflection, I mean like a mirror reflection. Like, let me just start with an example. Let's say we had our regular axes. And let's say we wanted to reflect everything across the y-axis, right? So maybe I'll actually change the color of the y-axis to something like that. Okay, so yeah, reflect across y-axis. And what this means is if I have some vector like here, this is my vector x, then the reflection will be the mirror reflection over here, right? So that will be t of x. And so t, this is still a map from, this is still a map from R2 to R2. And, you know, so let me pick a different vector. So like, if this is my, maybe I should have called this one x1, that's t of x1. And then if this guy is x2, well, t of x2 is exactly opposite, right? And it's worth noticing that maybe pick one more vector. Like if this is x3, that's along the axis, that's also equal to t of x3, right? The vector doesn't move at all. If it's kind of on the axis of reflection, it doesn't move. Okay, so that's the notion of a reflection. If we want the matrix, so again, the whole idea is to find the matrix of the reflection. Remember, what we do is we just see what happens to I hat and j hat. Or E1 and E2, as we call them, right? So if we have maybe if this is E1, then this is T of E1. So this is 1, 0. Then T of 1, 0 is negative 1, 0, right? It just reflects across. It's opposite. If we choose a different color for E2, 0, 1, then that also equals T of 0, 1. It's unchanged, right? And so there you go. Remember that the matrix of this is given by, the matrix has columns determined by what happens to the standard basis vectors. And so here, in that case, if we just replace this with this, right, because that's what that equals, and this with this, then we get our matrix. It's -1, 0, 0, 1. And that should make sense, because if you think about a point like x comma y over here, it should be taken to the point. Think about it. What's the coordinates of this point? Maybe pause, ask yourself. It's negative x comma y, right? And if you do t of xy, that's the matrix -1, 0, 0, 1 times xy. And that's clearly, if you just kind of do out the, however you'd like to multiply matrices times vectors, that's going to be -x comma y. So that checks out, right? Okay, so that's an easy reflection. But what I want to do now is I want to think about a reflection through a different axis, a different angle. So what if we did something like, it's sort of a generic, it's an example, but it's a generic example. So let's do this, the plane again. See if I can actually draw a vertical line. And let's think about reflecting across, say, a line like this. Okay, so I want this to be the line of reflection. And to specify it, let's just say the angle it makes is theta. All right, so so T is reflection across this line. Now, again, we just need to see what happens to I hat and J hat, or 1, 0 and 0, 1 vector, however you want to say them. And if we can write that down, then we can actually write down the matrix, but it's a little tricky. It's not too hard to figure out what happens to I hat, the 1, 0 vector. You can actually write down pretty easily in terms of theta and trig functions. 0, 1 vector, you know, there's like a 90 minus theta angle here. And again, there's ways to do it. It's not too bad, but I want to show you a kind of a new idea, a different technique. So instead of just like reflecting directly, I want to break this into a couple steps. I want to sort of say, like, this is a nice idea. Sort of, you can break this transformation down and do it. Basically, we're going to reduce it to a simpler transformation, okay? So instead of reflecting directly, this is going to be the idea. Instead of reflecting directly across this line, let's do something easier. Each of which, because each step is going to be something that we know how to do already. So here's the idea. Let me copy this picture. So here's a copy of this picture. Okay, and let's just think about, maybe I'll draw on this copy just something like the 1, 0 vector, right? So there's the 1, 0 vector. What I'm going to do first, the first step I'm going to do is I'm actually going to rotate the plane. And I'm going to rotate it by theta, but clockwise, to basically make the red axis horizontal. So you could really say rotate by negative theta, because that's going to be, you know, the positive direction of angles is like that, right? And so this would be like a negative angle. So rotate by negative theta. If we do that, the axis of reflection becomes horizontal. It's supposed to be a straight line. Come on, ability to be nice to me. There you go. So that becomes horizontal. And then, you know, I kind of want to think of the x and y axis as just always sitting there. So I don't want to move those. So maybe I'll still have a y axis here. That's not centered at all. And it won't make me a straight line again. All right. There you go. Okay, so, and then, but the real thing is what happens to the orange vector, right? The orange vector, which was I, now points down here with angle theta. So that's the first step. And the reason why I'm saying to do that first is because then now the next step is we can reflect across the x-axis. Right, and then if we do that, let me copy this picture. Let me just move it down here. All right, and then if we reflect, well, the orange vector is what changes here, right? So let me get rid of it there and just draw it up here. So, oh, the theta is still there too. I guess I should erase the theta. So now it's up here, right? And right, and the angle is still theta. And then the last step is to rotate back. And so we're going to end up with our axes. Again, I'm not sort of tilting I'm not rotating or reflecting the axes. I'm just leaving them there all the time. So there's the axes, but now our red line is sort of back where it was, right? It's sort of at this angle. I'll try to draw. I'll probably butcher a little bit. Well, okay, so something like that. So that's still theta, but now that we've rotated back, so that's by plus theta, then now the orange vector is up here where it should be after reflection, right? It's like up here somewhere. And so this really is t of 1, 0 now, because we've finally done the reflection. And it should make the same angle, right? And I'm only doing this because it's sort of hard to know exactly where the vector ends up. But each of these steps, I think, is pretty easy, right? Like, we know, actually, if we call these steps 1, 2, and 3, right? So let me just go down here. That's just picture-wise. But let's think about what happens if we start with 1, 0, and then do step 1 to it. Well, that's rotating by negative theta. So we want to multiply by the rotation matrix with negative theta. So that's going to be cosine negative theta, sine negative theta, negative sine negative theta, and cosine negative theta times 1, 0. But actually, if you think about cosine for a little bit, like you can even see it sort of pictorially, like the argument we used for the rotation before, that this really is going to have, this vector is going to have coordinates cosine theta and negative sine theta. And you can see that, like, the way that cosine works is it's an even function. So that minus goes away. This minus actually pulls outside in front. This minus pulls outside in front, but cancels that minus. And this minus goes away. So anyways, so I guess it's really the matrix cos theta, negative sine theta, cos theta. It's interesting that just the minus sign moved, the rotation back moved, and we multiply by 1, 0, and you can tell we're going to get the first column, right? Which is cosine theta and then minus sine theta. So after step 1, that's where we are. Step 2, we're going to reflect across the x-axis, and all that's going to do is it's just going to change the y here from negative to positive, right? Because we end up sort of below the x-axis, and then when we start below the x-axis, we end up above the x-axis. And so, yeah, step 2 is just going to change. It's basically going to just hit us with cosine theta plus sine and positive sine theta, which is nice. And then we rotate back. Now this is going to look kind of weird, but we're going to sort of, if we do step 3, we're going to multiply by the rotation matrix. This is the one step that's a little more complicated. So this is, we're going to take cos theta minus sine theta. Oh, you know what? I'm going to run out of room if I do it like that. So let me do it below. So step 2 wasn't hard. Step 3, we're going to actually multiply the result of step 2 times this rotation matrix, right? The result of step 2 is this vector I'm writing now, and then multiply on the left by the rotation matrix. And you should pause and write this out for yourself and see what you get. But what I get, if I do it, is cosine squared theta minus sine squared theta, and 2 sine theta cosine theta. Which is interesting, right? Again, like the second one would be like this dotted with this. So you get sine times cosine twice. But these are actually very famous. These are identities. In fact, not that you would necessarily remember them, but you might have seen them at some point in your life. This is actually the cosine of 2 theta and sine of 2 theta. And so kind of astonishingly, that's where 1, 0. This is t of 1, 0. And so that's really the first column of the matrix of this reflection is like that. Okay. By the way, this is not surprising if you go back even up to maybe up to this picture right here. I wish I could keep both on the screen at the same time, but this picture, look where this ended up. This ended up at exactly 2 theta. It's basically just the same as rotating by 2 theta. Rotating the 1, 0 vector by 2 theta. Like you start the 1, 0 vector and rotate it by 2 theta and you end up there. So that might have been a lot like more work than you think we needed, but I still like this idea of this is an important idea in math. Again, this picture right here of just taking something, translating it into something that's easy. It's almost just like tilting your head. You can think about rotating the plane, or you can just think about tilting your head so the axis is now horizontal. Reflect across that, which is a super easy formula, just changing the negative y to positive y, and then rotate back. And that comes up all the time in mathematics, actually. This kind of like change to an easier problem, solve the easier problem, change back. That's basically what we just did. So I think it's really cool. Comes up a lot. Now, what about 0, 1? Well, this, let me just do it faster now. So 0, 1, we're going to multiply by step 1. We're going to rotate again by this negative theta matrix, by this matrix right here. So, and in fact, you can already see we're just going to get the second column of that matrix because that's the whole point of multiplying by 0, 1. But let me just copy it out, except I don't use laser pointer. So this is the matrix cosine theta minus sine theta, cosine theta, times 0, 1, and that gives me just a second column, sine theta, cosine theta. Then we're going to reflect across the x-axis again, which is going to be making the y-coordinate negative. So that's going to be sine theta negative cosine theta. And then we're going to rotate backwards. So rotate, positive theta now. So if I write that matrix times the result from the second step, again, pause it, try to do it yourself. Tell me what you get. But now I get 2 sine theta cosine theta. And here I get sine squared minus cosine squared, which is very similar to what we had above, except we flipped cosine squared and sine squared. I'm comparing this to this. This is backwards from that. This is the same. And so in fact, this equals sine of 2 theta and negative cosine of 2 theta. Which again, you can sort of try to figure out geometrically why that works like we did with the first one, but there you go. That's the transformation applied to the 0, 1 vector. So the matrix of the reflection, we can write it down now. It's basically just, this is the first column and this is the second column. So therefore, the matrix for the reflection across the line at angle theta is cosine 2 theta, sine 2 theta, sine 2 theta, minus cosine 2 theta. Looks kind of similar to the rotation matrix, except for the 2 thetas and the minus signs in a different place. But it sort of does behave quite differently because reflections are quite different from rotations, but still there's something there. So awesome. So that's, I just wanted to illustrate that one technique of reducing to a simpler problem and then translating back. Translate to simpler problem, solve simpler problem, translate back. That's super important in math, comes up all the time. And I think it's really cool. And it let us solve this problem. You may not have thought that was super easy, but it's a very powerful idea, right? Okay, I'm going to stop there.